Greetings, guys. I'm Slikudis, and this is my first live stream using my voice, and I haven't made a live stream for a long time. So, um, I'm going to make the first implementation of Mattbatwing's BatPu2, but and with pipelining. I'm gonna use four stages: fetch, decode, execute, and write back. Plus, it's gonna be the second second implementation of that CPU. But on System Verilog, I was the first and only person to implement that CPU on System Verilog. I did that 2 months ago. The problem with that implementation was that it couldn't use an Intel the block RAM of the FPGAs because it takes one clock cycle to fetch data from those block RAMs. But I need I don't want to I don't want to waste logic elements for the RAM. So pipelining will make this implementation much faster and it will support block RAM. I'll be right back. I'm back. So first, we have to make a to-do list. So I have already made two modules, the fetch stage, which I took from my System Verilog implementation of my architecture called SRM. Implementation is called S1. That implementation where I played Bad Apple. Well, not exactly, because that was the unpipelined implementation, but it was used on the System Verilog implementation. Then the register file, also taken from the pipelined SRM S1, and I modified it to use 8-bit data and 4-bit addresses. But it will still support forwarding and the zero register. And so for the see the instruction ROM and the control lines have already planned them, so the design process can be easy. This, the first three bits are for selecting the LU operation: add, subtract, NOR, and XOR, right shift, and be in. This one specifically is used by the load immediate instruction because I'm gonna select the input B of the LU as immediate instead of register source 2, and I'm not gonna update the flags. So instead of having to make a bigger multiplexer for the data in of the registers, I will just need one for the LU and one for memory. So let's see. We are going to make a to-do list for designing. Have already made the fetch stage. Now we have to make a decode stage, and then the execute stage, the write back stage. So we are right now at the decode stage. We are not going to make an instruction register for the decode stage because we can already use the output buffer register from the block RAM, because as I said previously, it takes one clock cycle to get the data from the block RAM. So let's see, it got 18 control lines, so output is gonna be called control word. Now we are going to make the label for the instruction ROM. Let's design the instruction ROM for the implementation. So we're going to use an always comp block and use a case. In this case, we are gonna use case opcode. Now let's start. Case 0, hex 0. No, case 4, hex 0. 4 bits with the hex value 0. So let's see. This is no op. When I'm going to show you instructions at table. So you got no op, halt, add, subtract, nor, and XOR, right shift, load immediate, add immediate, jump, branch, call, return, load, and store. So let's start. Let's do these instructions in order. No op. The control word is going to be equals to 0 because nothing happens. You have to assign control word as a logic. I'll be right back. I'm back. So, no op, nothing happens. So, the control word is going to be 0. Then do halt. So halt holds the clock in the CPU, and we got a specific control line for that. Clock halt, which is line 18. Well, logically 17. So let's see. 18 be 1 for halt. Let's also divide the bits by category because we got selection bits. This is going to make organization easier. see steering, select destination selection, write to the registers, write to memory, request from memory, input of the program counter, branch, jump, update flags, select immediate, select operation of the LU, and now select input B of the LU, and then select operation of the LU. Let's count 0, 1, 2, 3, 4, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So this is our control word for halt, and this one for no walk. Now let's see the next instruction. So our next instruction is add. So add basically adds register A and B and stores the result on Z, and also updates the flags. So this instruction first doesn't halt the clock. The input of the registers is going to be the LU. The destination is going to be C, selection 2. Then we are going to modify the registers. We are not touching memory. We are not touching the program counter. We are not we are not touching the program counter. We are touching the flags. We are not using immediates, so we don't care about that. We are selecting register source B or RS2, that's how I call it, because I want to maintain this in a serious way. And then operation, this operation 0, so this 0. And we call this add. Now we can go with subtract, which is this one. Subtracts register A with register B and stores the result on register C. It also updates the flags. All these operations update the flags. So they behave in a similar way. So we just have to copy and modify the first argument here. 3, 4, 5, 6. Add, subtract, and no, nor, and XOR. And then you only have to change these arguments. Now we are going to make right shift. So this one is similar to these other ones. It uses the LU but doesn't update the flags. So we are going to set this control line to 0. Let's see the next instructions. Load immediate and add immediate. So, see, for load immediate, we are going to select immediate 8 and here select immediate in the LUV input selector multiplexer. So let's see, behaves similarly to right shift but with some modifications. So the operation we are going to use in node immediate is going to be in, doesn't just output input v from the LU. So I call this load immediate. And then we are going to select input b. So we got our load immediate instruction. Let's see. And another thing we have to do is select the destination as A. So we set this to 0. Now for add immediate, it's the same thing as load immediate, but it updates the flags and uses addition. So the flags aren't are updated here. So we got add immediate. Now let's check the next instruction. Jump, we have the branching instructions, jumping instructions. Jump, branch, call, and return. The easiest one is jump. So for jumping, we don't care about these lines here. What we care about is updating the program counter. So we go to jump, which is line 6. 1, 0, 1, 2, 3, 4, 5, 6. No, wait. 1, 2, 3, 4, 5, 6. No. 0, 1, 2, 3, 4, 5, 6 here. So this is the only thing that jump has to do. It only toggles this control line. And then for selecting the input of the program counter we use this. But let's see jump instruction. The argument, the operand is this address, a 10-bit address. This one here, and it's selection 0, so you don't have to do anything special here.
I,
Hello, who's there?
you know you were all alone?
Yes, I know, but I'm live streaming, so.
Oh, okay. What language is that?
And it's called System Verilog. It's a hardware description language used for designing ASICs and FPGA implementations. And it's not like making normal schematics. The problem with those is number one, the messy wiring, and number two, the slowness. So I'm trying to make the first pipeline. Right now, I'm trying to make the first pipeline, the implementation of Mattbatwing's BatPu2, but okay, the first pipeline
Good
implementation.
luck.
Oh, thank you. Uh,
I don't know what it is. I'm probably going to go to bed like 1 a.m. and I'm just dead.
yeah, I
And I just
understand.
fucked up my redstone project.
Oh,
Oh, hello.
Uh, I realized on Matt's server instant redstone wires work.
I see. So that's
Yeah,
happened to the
so
live stream. We have finished.
I
Goodbye. So we have finished jumping. Now let's go with branching. What what branching does is that it selects a condition, in this case, from the flags equals, not equals, greater than, and less than. And in the more specific translation, equals is if 0 is equal to 1, not equal if 0 is equal to 0, greater than or equal if carry is 1, and less than if carry is 0. So the reason it's that way is that got a compare to the instruction that subtracts A and B, stores the result, and register 0. So basically, that result is thrown away. It doesn't matter. We only want to compare A and B. So the flags are useful for this. So let's see. We have branch. And the control line for branch is control line 7. So the reason I'm using control line 7 is that I'm going to make a multiplexer connect these two bits from the instruction bus to that multiplexer, and that multiplexer will select the condition. And we connect the output of the multiplexer with the branch control line, and the and line is going to be ORed with jump. Now let's make the jump. By the way, we are going to implement a basic branch prediction system, a static branch prediction system in which branches are going to be accepted if we are jumping to a value lower than the current value of the program counter. That's useful for loops. Or if or there's a chance I'm going to change my mind and use bubbling always. So let's see. Control word. Now we are going to use to make the call instruction. So this instruction pushes the program counter into a stack, an internal stack, and then we set the program counter to this new address, just like jump. But and what happened? Why do we have a stack in our CPU? That's because we got a return instruction. So when we finish executing a function subroutine, we and we execute the returns instruction, and this one and sets the program counter to the value at the top of the stack, and then and and that's all. It pops the top of the stack into the program counter, and the next value of the stack is ready. So let's see. For call, we, we don't modify, we don't hurt the clock, we don't we don't care about the registers, and we don't care about memory. We care about the PC. Yes, input is going to be 0. Then for call stack type, also 0, which is push. because we are pushing the PC onto the stack. Then we use call stack exe, which activates the call stack. It enables the call stack. Then we don't use branch because it's not conditional. We use jump. Then we don't care about the flags. We don't care about anything else. So this is our call instruction. Now let's know the return instruction. Wait a minute. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oops. 11, 12, 13. Okay. Control 1. Now we have to make our return instruction. So grab this, put a comment, return. So it's an unconditional jump. Yes. It's not branching. We use the call stack. We pop from the call stack and we select our input to our program counter as the top of the call stack. So we got our return instruction. Now let's see the next instruction. And our next instruction is memory load. It sets the register B, to the contents of memory indexed by register A plus assigned offset. So, how do we calculate the effective address? We are going to use the LU itself. So let's see.
Hello,
Hello.
it's me, Stevius. I'm on a different account now.
Nice. I'm live streaming about my pipeline implementation of Mattbatwing's CPU, but on System Verilog.
Yo, you should put it on GitHub.
Yeah, I will definitely do that so everyone can see it. And
Yeah,
say hi to the live stream. I don't know if anyone is here. Let's see, but
I'm watching the live stream.
nice. So let's see. So we are right now making the load instruction. So register input is going to be 1 because our input is memory. Then for the destination selection, we're gonna use 1 which selects operand B. Then we go to the registers.
Nice. Swear to God, I'm never gonna understand that System Verilog
Don't worry. I will
someday.
still explain everything on the live stream. So right now I'm making the instruction decoder, and these are the
Uh-huh.
controls.
Yeah, so this the control unit or the control ROM.
Yep. So
Okay, yeah, makes sense.
these 3 bits are for selecting the operation of the LU. This bit is for selecting the input V of the LU, basically multiplexing it. We got
Yeah,
and register V and immediate. Then this one is for selecting the immediate. We got immediate 4, immediate 8, then normal immediate, like here, and then immediate 4, which is the offset for for the addresses. Uh, we got this one that updates flags, this one for jumping, this one for branching, this one for activating the call stack, this one for selecting the operation of the call stack, this one for selecting the input of the program counter, this one for requesting for memory, this one for writing, this one for writing to the registers, this one for selecting the write destination of the registers, this one for selecting the input of the registers, and this one for halting the clock. Um, so we are, let's see, halt, register in, destination selection, register write. Okay, this one is memory request. So we request to memory. Then we got PC. We don't care about that because we aren't jumping or branching. So these other lines, we don't care about them until we reach the ones for the LU. Right. Right. These ones. So we for the immediate for we select immediate for because we are using the small offset. Then for the input v of the LU, we are choosing immediate, and then we are choosing the operation to add because the address mode is displaced addressing in the end register plus offset. And we got memory loading. Now let's do our last instruction, which is memory storing. So this one doesn't use the doesn't stop the clock, doesn't care about the writing of the registers, so we can skip that. Then it writes to memory, that's important. Don't care about anything else. Here we see the part of the LU. So it also selects immediate, this immediate for selects input v as immediate. Alright, we call this store. So we got our control ROM finished. In this case, instruction ROM because I like calling it like that. In case, and we are going to name this block ROM logic. Now we got our control ROM. So let's check we got any problems, and we got 0 problems. Now let's design our LU. So we are going to first make the combinational circuits and then the sequential circuits, which are the stage control units. So we got declare the module LU. We declare the inputs. Input 7 down to 0 A and B. Output 7 down to 0 res. This one will output the result. Let's see. So we are going to use an always com block. So when I declare res as a logic, always com begin, and we are going to use a case. Oh, I forgot. Input 2 down to 0, a 3-bit input operation. So pay attention at operation. I'll be right back in a second. Alright, I'm back. So let's continue. So operation 0 is add. So res equals. We are not going to use a plus b. Want to do an optimization. I want to make another the subtractor. I want to make another slash subtractor. So we are going to declare wire 7 add sub equals a plus b XOR extended operation 0 plus
Yo, hello.
hello. Yo Gnocchis making a live stream about my implementation of a System Verilog BatPu2, the, the second System Verilog implementation ever, plus the first implementation ever of a pipeline BatPu2. So I'm probably no one is watching the live stream from YouTube, but I still want to make it, want to improve my communication skills. So this is another addition slash subtraction depending on the first bit of operation. So and res equals add sub res also equals add sub. I'm going to put comments here. Add sub here is null, so um, a or b is a not operator here. Nor and here res equals a and b and res equals a XOR b res equals a right shifted by 1. Just in case the synthesizer doesn't want to cooperate, we are going to use concatenations. Then here res is equal to, let's check the instruction ROM, be in. So it's just b. And default res equals 0. We in the case end the block. We give a label to the block. And we got our arithmetic logic unit. We can make a test run to test this thing. So I'm going to make a folder, call it test bench, and here I'm going to make our AU test bench module. So input clock enable, and sync reset. So let's see. Make a reg called reg called up. Then reg okay no. I'm going to make a reg called timer. Then a reg no then logic called a. Logic called b. Logic called op, and the wire called result, so we can see what happens. Now we instantiate the module. So what we are going to do is type lu, call it lu inst, and here put dot a from the lu is connected to a from here. So we make the connections for every part. And we instantiated the module. And now we are going to make our logic for testing. So making always ff block at positive edge clock begin if clock enable begin if timer equals 0 begin. OP is going to be 0. Okay, no, always FF is going to update the timer. Then here I'm gonna remove this, put it here. Move this to an always come block. OP equals 0 addition, A equals 2, B equals 5. We use each testing case. Now if timer equals 1, OP is 1 subtraction. A is going to be 10. B is still going to be 5. So we are going to do 10 minus 5. Now, copy this over again. I'll be right back in a second. Okay, so back to coding. Let's see. And let me copy this. No. If timer equals 2, then now p equals 2, a. Okay, so this one is NOR, so let's use some hex values. 8 hex ff NOR 8 hex f0. And if timer equals 3, and operation equals 3, and this one is AND, use the same values. And here we perform XOR. Let's also use the same values. And then we are using right shift. So let's try 0 hex 8. It should be converted to 0 hex 4. Don't care about B. And then let's do operation 6 transfers input B to the result. So we don't care about this. So put B as 7 to test. And we got our always come block. So let's see, let's check the terminal for any problems. Ignore this one because okay, now we set the test bench task here. So go to configure default task. No, wait. No, again. Configure default build task test bench clean. Now let's go back here. We test it. So I press Ctrl Shift V and pray for. Okay, so let's see what errors we have. Null port on module. So I forgot about this comma. Close this again. Okay. Okay, another issue that I accidentally created. Okay, let's check the errors. Okay, I used 30. I used 32 bits because I'm used to design 32-bit CPUs, these are implementations. Okay, another thing should have been 3, not 4. Let's try again. Okay, what other errors do we have? Expect 21. Okay, that's not good. Now wait. Okay, this doesn't make any sense. It expects 24 bits. Maybe if okay, how does it expect 24 bits? Doesn't make sense. Oh, okay. That's inferred. Okay, no errors. Now let's test this. So we first look at the clock and clock enable signals. Then check the timer. Alright, we're going to see it in decimal. Now the operations. First look at the inputs A and B. Data format decimal to start with. And now at the result and operation. So let's see. 2 plus 5 is 7. Addition works. 10 minus 5. Okay, now that's not supposed to happen. I accidentally sign extended instead of 0 extended one section. So we got to the LU here. I sign extended OP from 1 bit to 8 bits. So that's not good. What we have to do is 0 extend, so we put 7 zeros, comma, OP. Now let's restart our test bench. Here. Let's see. A 2 plus 5 is 7, correct. 10 minus 5 is equals 5. Now it's correct. Let's see. FF nor F0. Let's check that part. FF or F0 is FF inverted 0 0. So it's correct. Let's check the AND operation. And FF and F0 is F0, correct. Now FF or F0 XOR F0 is 0F. And that's because these two first nibbles cancel each other. Now right shift, let's see. Okay, another error I got. The AU. It was a bad concatenation. Let's see. We got clock enable. We don't maybe we should only pay attention to operation A, B, and result. We don't care about the other parts. Okay, let's go to operation. Right shift. So it worked. We can visualize this in binary so you guys can understand better. So this is the input value and then the output value. This bit was shifted to the right by one space. And then we got transfer V to the output and it worked. The input V was 7 and result is 7. So the arithmetic logic unit works as expected. We have fixed our bugs. And now we can perform addition, subtraction, NOR, AND, XOR, right shift, and transfer B to out. So, in the progress check, we got AU. Let's make a better list. Now, let's look for the odd list. Fetch stage, done. Instruction decoder, done. Okay, no. Decode stage, unfinished. Let's make a sublist. Instruction ROM, finished. Okay, done. Then path logic unfinished. Then the execute stage. AU done. Path logic unfinished. Now in the write back stage, we just write You also have to implement in the code stage branch predictor. So we are going to use static branch prediction and bubbling. So the decode stage consists of decoding plus sampling slash branching. So and if the jump control line is active, then it's going to automatically update the instruction pointer of the PC. We we basically save time. Our pipeline is going to be full, and that's good. Then and for branching, it's a special case because we are checking for the conditions at the execute stage. And why not connecting the flags to the decode stage? That will make our signal first, and the signal, and it's going to take a small time for the signal to get from the execute stage to the decode stage. But also because it's because I want to make my first branch predictor. So if the prediction was true, then nothing happens and the code continues executing. But if it wasn't true, then we apply a bubble. We apply, we apply a bubble to the from the execute stage to the decode stage, and we also update the program counter. So let's see. No, wait. We are not using branch prediction yet. Decode stage, we perform branching. I'm going to apply branch prediction to the S2 implementation of the SRM. So now, right backstage, nothing special. This is our list of things to do. We got AU, instruction ROM, and the fetch stage. Now we have to make the path logic of the decode stage and the path logic of the excess stage and the whole right back stage. So I will continue doing that tomorrow, guys. So it was a nice time. I think it was a good first live stream, in my opinion. And I promise to improve my communication skills for the next live streams. This is a new thing for me. So thank you for watching, and I hope you liked this live stream. I hope Mattbatwing finds out about this. It will be very nice. I would like to show Mattbatwing himself the first ever implementation of his CPU, but with pipeline. So, goodbye, guys. See you.